So, okay, I guess we will start, and I hope some more people will join meanwhile. So once again, can you hear me properly?
Yes, yes.
Thanks, because I had troubles with my microphone in the morning. So my name is Oleg. I will teach you Introduction to Mobile Robotics and Robot Operating System course. So today we have our first lecture. It's going to be introductory. I will tell you how course is organized. And then the second part of the lecture, we will start discussing like robots in general and which types of robots are out there, and eventually we will come to mobile robotics and what mobile robot is. So as I said, you can scan QR code and open slides on your device. I will distribute slides and lecture after the lecture. We'll use for that PIAZZA system. I will tell you more about it later. So this course is going to be organized in two parts. The half of the course, half of a term, we will talk on robots in general, and we will learn robotics theory. We will talk about localization, mapping, path planning, control. So the first half of the course is going to be theoretical. We will see which types of algorithms are used in different fields of robotics and so on. And the second part, which will start, I guess, in April, will be dedicated to robot operating system. This is a framework, programming framework, which is used worldwide for robots programming. And we will talk in details what the history of robot operating system. We will see how program robots using robot operating system. We will have like live coding. So this is the course division. So first half of the course is going to be theoretical. So my aims are to give you an overview of the robotics, because robotics is really, really broad. There are many areas of research. So I want to present you a modern algorithms of mobile robotics, and I will tell you why mobile robotics, well, exactly this area is so interesting right now. Also, we will discuss a lot probabilistic robotics. This is a like main paradigm for programming and creating robots at the moment. And we will discuss why we have to account for probabilities when we are talking on robotics. So also, of course, I want to give you a practical experience of programming robots. For that, we're going to use robot operating system, as I said. It allows you to program robots even if you cannot afford to have like expensive real robot. It allows you to use models and work with the models as with a real robot. So we'll have one lecture each week in 9:30 in Tuesday. Actually, if there is some another time which is convenient for all of you guys, we can discuss it, and we can switch the time for the lectures if all of you will agree for some another time. So during the course, we will have 3 homework assignments, 1 team project, which you have to present in the end of the course. Usually it performed by a team of 2 or 3 people, but it's discussable. So there can be more or less people in the team, but the main point here is that it is has to be a team. So 2 people minimum. And in the end, we will have an exam, just 2 questions, 1 theoretical from first half of a course and 1 practical task from the second part. So as for homeworks, here you can see 2 of them. As I said, there are going to be 3. So 1 will be dedicated to localization. So given the sensor readings, you will have to determine where robot is on the map. This is the first animation, and the second homework will be dedicated to control. So you will have a simulator like that, and you will have to program the robot or the car to follow the middle of the road. So as you can see, the car is waving a bit. So you will have to try to program a car in a way so it stays on the road and like runs the whole lap of the racing track. So, and there are going to be also third homework. I'm still deciding which one. Maybe it's also going to be about positioning, but I will tell you later some details on the third one. So as I said, there is a team project. I think you will have to come up with a topic by the end of February. I'm preparing the list of possible project topics. So I will give you some project topics which you can choose from, but you also can come up with any robots relating topic to work on a project. So if you are taking some parallel course and there is something which can be applied to robotics, you can also come up with some topic and perform project which is related to your other course, for example. So we will discuss it later in more details, but you can reach me anytime and propose some topic for a project and we will discuss it. So this is just, these are just two projects from last year course. One was about building a height map of the environment. So on the top of the slide, you can see there is so-called stick cells. These are these vertical bars detected in a stereo image. And then guys from this team were building the map of height of environment given those stick cells. And another project was to build again a map from an evacuation plan. So guys collected data set of such evacuation plans, performed some computer vision algorithms, and again they were able to build a map given which robot was able to navigate in the environment. So these are just examples of team projects. Regarding final score, you can see here, and also I will send you a syllabus. So 30% for home assignments. So each home assignment gives you 10% of a final score. Team project is 30% and exam is 40%. And scores are rounded in favor of student. So 7.5 is equal 8. And yes, this percent are mapped to from 0 to 100 directly, and then divided by 10, you get your final score. Yeah, by the way, you can interrupt me anytime. You can raise your hand in Zoom or just switch on your microphone and start talking. It's okay. I prefer this course to be as interactive as possible, so just don't hesitate to interrupt me anytime. If you have questions, you can ask them right away. Any questions so far? Okay. So as I said, we will use PIAZZA, and also there are going to be a Telegram group. So in this presentation are the links you can use to go to PIAZZA and Telegram. Maybe somebody can just join Telegram right now and invite others later, so it's going to be more convenient. I see that somebody joined already, right? So yeah, just I'll ask you to invite all other students. Yeah, and maybe that's the right time. If you wanna have your slides on your device, you can scan QR code right now to use the links to PIAZZA and Telegram. So in PIAZZA, is anybody familiar with PIAZZA? Maybe you used it in other courses, no? So this is a system where I will put all slides, homework assignments, project proposals, and any materials of the course. It also contains chat, so you can ask questions in PIAZZA, but maybe it's just more convenient to use Telegram. That's why we will use both. So syllabus are also in PIAZZA. So that's really convenient system for course organizing. If you will have any questions or problems joining the PIAZZA, just text me in Telegram, I will answer, or ask in Telegram group, maybe somebody of other students will help you. So starting talking on robotics, we first have to determine what robot is, right? So robot is actually a Czech word and it means slave labor. And according to Oxford Dictionary, robot is a machine, especially a programmable one, but not necessarily, which is capable of carrying out a complex series of actions automatically. So as you can see, the definition is really vague and like broad. So anything can be robot according to this definition. But it's interesting how this term first was introduced. There was a Czech writer, Karel Čapek, and he just came up with this word in his play, which was written in 1920. And the play was about like artificial people which were created in factory and which were basically slaves performing some tedious work instead of people. And this is actually a really interesting play. You can see it still in some theaters, or you can just read it. I really suggest you to read it because it's like really, really impressive, and it has open ending. So we can see this even Oxford definition is really broad. So we will try to talk about robots containing three main parts. So for me, robot is something that performs three main actions. Perception, so it can perceive world around somehow with some sensors. It can also perform actuation, so it can interact with the physical world, like move objects, maybe touch something. And also definitely a robot is something that performs computing, some types of calculation or like thinking process. So for these three actions, robots are equipped with three different parts: sensors, actuators, and computers. And all these three parts are really important and cannot exist and operate one without another. And it is interesting that when we talk about computers, we often imagine like modern computers, right? Like something electrical, which works with current, like and can perform some computations, but it's actually not always the case. For instance, NASA has a project where they build fully mechanical robot. So it only consists of like gears basically and mechanical parts, but it still can perform some computations. So basically it has a computer. And if you ever been to some technical museum, they always have these calculators which are purely mechanical but still allow you to perform some computations. So computers is not always something like modern and electronical as we imagine. The same applies basically to sensors and actuators. So still it's not really clear what robot is. And actually on the slide you can see my washing machine, and one day it just turned to mobile robot. It just started moving. And that's actually an interesting question. Can a washing machine be considered as a robot? As we said, it has to have some sensors, actuators, and computers. And obviously washing machine has all of that. It has some temperature sensors and encoders because it knows the temperature of the water and speed of rotating, right? It has computers definitely because it has buttons, it has different modes of operation, and it has actuators because there is some motor inside which can just rotate it, right? So according to our definition, and especially to this really broad Oxford English Dictionary definition, washing machine is a robot. And the same applies to electric kettle, satellite, or C-car, automatic transmission in your car. So how do you think, how can we distinguish robot from just appliances? Any ideas maybe? Come on, don't be shy. Maybe somebody knows. So my version is, I would say that robot is something that has all three of that, sensors, actuators, and computers, but also something that has operating area outside of its body. So a washing machine and electric kettle, for instance, they interact with physical world inside themselves. So we have water inside the kettle, and we have our clothes inside the washing machine. So they have an interaction with the physical world, but only inside their body. And usually those considered to be more appliances than robots, but still it's really depends. So among these, I would say that satellite is definitely a robot, and automatic transmission is definitely a robot. Considering RC car, it depends really, because not every RC car has some sensor. So sometimes they're just remote controlled cars which do not have any sensors, so they cannot be considered robot in this case. But it's important that there are some robots which are remotely controlled. So remote control is still remotely controlled mechanism are still can be robots. And there are many robots, especially in space, which are remotely controlled, but they're still robots. So as you can see, the definition is really broad, but usually we are able to tell either we see robot or not, but there are some corner cases when it's not that easy. So there are many types of robots. As you understood already, this course is going to be dedicated to mobile robots, but we will still discuss a little bit which types of robots are out there. So first of all, there are aerospace robots. There are many of them on the slide. All of them are unique and different and interesting. For instance, on the left side of the slide, there is a Curiosity rover, really famous. I guess you heard of it. So such rovers can be autonomous, and they also can be partially remotely controlled. They're used to discover some other planets and other space objects. What's interesting about Curiosity is that this was one of the first rovers which used visual odometry. This is a really powerful technique in robotics. When using just only single camera, we can determine where a robot is in the space relatively to our starting position. And so this technique was firstly applied in space robots, and then every modern autonomous car or autonomous robot with a camera uses this technique. There are also many more interesting robots. On the right side of the slide, there is a so-called Robonaut. This is a NASA project. They use this robot in a space station. So they launched it already several times to a space station. It is built in an anthropomorphic way, so it can operate with all the appliances and tools which are created for people. And there is also a really interesting story about this robot. Firstly, it was sent to space station. It got broken like in a couple of days. And since there are no roboticists on the space station, there are engineers, but they're from other fields. They had to fix it in place in the space station. And so what NASA came up with, they started like online translation from Earth to space station, and they taught engineers on the space station how to fix robot online, and this operation took more than 24 hours. So within 24 hours, without interruptions, they were fixing this really complex robot on the space station, and they succeeded partially. So it was operational, and the mission was conducted in the end, but it took them 24 hours online to fix the robot. So there are also industrial robots, and I hope you recognize this really famous factory. This is a Tesla factory, which they show really often. They use a lot of robots in cars production, and many operations are automated. So industrial robots are usually used on factories for some dangerous or complex operations, or operations which require really high precision. So these robots are usually really expensive because they use really precise motors and sensors to perform this precise operation. So as you can see, they can perform welding, some types of sorting, many more operations. And actually the industrial robots is the most common type of robots in the world. So like 70% of robots in the world are such types of robots, basically manipulators or different types of industrial robots. So there are also medical robots. Here you can see a grape where this robot called Da Vinci performs some surgical operation. So these robots are remotely controlled by operators. So there is a doctor performing operation. This robot is also very precise because it is used for such precise types of operations. And actually we even have a couple of such robots in Moscow in different clinics. And on the bottom of the slide, there is some mobile robot, which used I guess in United States, this one particularly, to distribute pills in the medical hospital. So it just travels around the hospital and distributes different types of medical pills and things like that. So there are drones, and I think you all have seen or used drones. There are many types of them, not only quadcopters, which are popular in the last decade. There is, for instance, this huge drone is from Google, and it uses solar panels. So basically, this one can travel around the world without landing due to this solar panel it uses. And it used to study ionosphere to make a more precise weather forecast, basically. So yeah, as you can see, there are even swimming drones. So they're balancing drones, and drones is a really hot topic right now. So there are also so-called extreme robots, and the field of robotics called extreme robotics. Those robots are used for so-called 3D jobs, dirty, dangerous, and demanding. So basically jobs which we are as people wouldn't prefer to make. So on the left slide, for instance, you can see robots used in Fukushima. This is nuclear station disaster which happened in Japan. And they applied many robotics solutions to fight basically with the disaster, to search for people, to check radiation and so on. So there are also underwater robots also used for dangerous areas, for example, for monitoring. Many kinds of robots. Such robots are usually teleoperated or remote controlled, as you can see on the slides, on the animations, because they operate in really, really complex environments. It is sometimes really hard to make them autonomous, to make them to decide autonomously how to move through this environment, how to perceive it, and so on. So these types of robots are usually remote controlled, but it doesn't make them less sophisticated. So obviously there are military robots. You can see, I guess you recognize some robots from Boston Dynamics, but it is interesting that this walking robot in the bottom right corner is also a robot from Boston Dynamics. This one was built to check actually military clothes. So they built a humanoid robot to study the clothes for military, to study how convenient these clothes are, how durable they are, and things like that. So Boston Dynamics is famous not only for such four-legged robots, but also for such types of robots. Many military robots are used to fight with some types of bombs, and as you can see on the right top animation, this is actually from a movie. I don't remember right away how it is called, but this is from Hollywood movie. Okay, so there are also educational robots for kids, and not only. For example, I started my path in robotics from such a robot, dancing one. This is called Nao. This is from French company called Aldebaran. And this robot is actually really cool. There are many researches and scientific papers which are used these robots for some research. It actually has 28 degrees of freedom. Even though it's really small, it's really complex. You can perform really interesting moves and actions with this robot. And it's also equipped with many, many sensors. So this is a good research platform if you're interested in humanoid robots. There is also famous Lego kits which can be used to build real robots. This is one of the fastest robots solving Rubik's Cube. There is actually the whole competition of building such types of robots from Lego. This one solves in like 5 seconds. This is close to world record actually. There are also entertainment robots. So there is a robotics band you can see on the slide, and this band actually gives performances all around the world. You can buy a ticket and go to the concert of a robot band. And again, this is actually really sophisticated robots which can really operate with guitar and any other musical instruments. There are some more like around toys robots, but still they're quite complex. So what's more, there are exoskeletons, and there is actually a big discussion either call exoskeletons a robot or not, because it's just some type of mechanism. But again, it has actuators, it has computers, it has sensors, so it can be called a robot. And these exoskeletons are used to empower people to, for example, lift more weight that usually people can. Also, they're widely used for rehabilitation after some, so for people who got into some kind of trouble, they are used for arms, for legs. There are several companies in Russia, really well-known ones, for instance, Exo which are building such types of exoskeletons. So there are anthropomorphic robots basically which work and operate as human. This is a really complex thing and still really expensive, even though like Honda has this really famous robot which really works well and can walk. Boston Dynamics has their Atlas, which just incredible in terms of control and balancing. But still, these robots are not really used for practical cases because they're complex, they're expensive. So this is a still open area of research. And as you can see, they're really clumsy sometimes. So there are many, many videos you can find on internet when these robots are falling down. And even Boston Dynamics tells everybody that these incredible shots they get them not from the first time. So it takes them many trials to make this shot, even though their robots are the best in the world, basically. I mean, anthropomorphic ones, definitely. So there are marine robots, any types of operations underwater. Again, there are remote controlled ones, autonomous ones, robots which look like people, robots which look like snakes, fish, and any type of animal. So there are many, many types and forms of underwater robots. They're really used for practical cases to perform research, underwater research, before building some types of pipes or communications underwater. They're also used to investigate the landscape and things like that. Like couple of years ago, there was a boom of telepresence robots. So basically, as the main idea here is that you can be somewhere else just using zoom on the wheels. So basically, any telepresence robot is some type of mobile robots which you can control remotely to move through the space. And it always has some screen which presents you and camera so you can see surroundings. And the main idea here is that you can attend any like lectures, classes, meetings, just by using this robot. Well, as far as I know, this is still not really popular, even though there are many, many companies working in this direction. So there are still not that many of such types of robots. My favorite type are autonomous cars. I guess you all have heard of them, have seen these cool videos. Many companies working on autonomous car nowadays. Like in Russia, there is at least Yandex, there is Waymo from Google, and actually this small cute car is from Google, from Waymo. Those videos on the bottom on the right from Tesla, which are kind of different from all other guys. They're using only visual sensors for their cars, which is quite complex. So, and actually, this is the closest category we will discuss in this course, because this course on mobile robotics and basically on wheeled robotics. So all algorithms we will discuss in this course are applicable to autonomous cars and are really used in autonomous cars. So there's the whole field of bio-inspired robots. This is when we try to replicate what nature created in our robots, because there is actually really, really cool things in nature and different types of animals which we would like to have in our robots. There is a really cool company called Festa. So Festa is actually a company creating any type of pneumatics like equipment. But every year they come up with some type of robot which use pneumatics. So these two, kangaroo and the bat, they use pneumatics from Festa to operate. So every year, to promote, Festa company builds one type of a robot looking like animal. They already had kangaroo, butterfly, bat, spider, and many, many more. Just Google Festa robot and you will be impressed how cool robots they built, even though they're not robotics company. Their equipment is used in robotics a lot, but they're not robotics company. But this is really fascinating which robots they built. I recommend you to Google Festa robot and to see some cool videos. So there are also robots which operate as birds, fish, and many, many more. There is some cool worldwide known laboratories, one in Switzerland, one in United States, which only work on bio-inspired robotics. So they discover some animal properties and try to replicate them in their robots. So one of the modern areas in robotics is soft robots. As you could see, many robots we usually see, they're still built from metal, and it really limits their capabilities, because many things can be performed only by a soft mechanism. And actually our tissue is soft and our limbs are really flexible. So there is a research area of soft robotics which try to use these soft actuators, which actuated by usually air or some other type of gas. And they have really cool results. So you can see that there are soft manipulators which allow you to operate with really fragile objects without destroying them, because it's really difficult with metal and plastic to operate with fragile objects. You have to come up with really sophisticated control algorithms to control such types of manipulators and not to destroy objects. For instance, I know the lab in Germany which spent like the whole year trying to teach industrial manipulator to operate with an egg. They were building some automatic kitchen. The idea was to cook different types of dishes with robots. And they really spent the whole year to teach such a robot to operate with an egg without destroying it. It's really complex. Even though for us, for people, it seems like a really simple task, for robots it is not. So the really, really new research area is called tensegrity robotics. Tensegrity means like combination of basically wires and hard objects. And you can see that those robots are really weird and moving in a weird way. But they became popular because due to this tension and compression, they can turn into different shapes. And this allows them to overcome really difficult terrain. So these robots came from aerospace field, and they were firstly created for like Mars discovery again, because the terrain on Mars is really complex and you cannot use just rover with wheels to overcome some terrain there. You cannot always like overcome some rocks and stuff like that. So for that, engineers came up with tensegrity robots, which are moving really slowly, but because they're so flexible, they can overcome really complex terrain. So this was a short overview of robotic fields. Maybe you have some questions right away on some types of robotics. Okay, no questions. So then we will go further and we will see which types of locomotion are there in robots. Locomotion is a type of movement. So there are wheeled stationary robots. So as you can understand from the name, stationary robots are not moving at all. Wheeled robots are used wheels to perform locomotion or movement in space. There are flying robots, crawling, swimming, walking, and you have seen all different types on the images on the slides. So there are some examples, tracked robots as well. There are other types of robots. For instance, this robot is called Tarzan. This is a robot which used to check wires. Basically, this robot can monitor wires. If there is some damage, it can tell. And it uses two different manipulators, two different arms, basically, to walk over these wires. Because that's why there is category called others, because there are many weird types of robots using different kinds of locomotion. But the general ones are wheeled, tracked, walking, flying. So in this course, we actually will talk on wheeled robots. Even though there are different types of locomotion, wheeled robots are the most common at the moment because they're most simple and most convenient. So wheels are really cool mechanism which allow you to overcome different types of obstacles, terrain. You can see the autonomous cars evolving. You can see vacuum cleaners which also use cars. Basically, all algorithms we will discuss during this course are also applied to tracked robots and mostly apply for walking robots, any type of robots which use path planning, localization with some peculiarities. So the general like algorithms are applicable everywhere, but there are some small parts of these algorithms we will discuss. You have to tweak to use it in different type of robots. But as a like reference, we will think on wheeled robots during this course. And here I wanted to make a small off-topic talk on like why actually I'm telling you about mobile robots and why mobile robots are so important for me, and maybe just make a small PR, maybe somebody of you will be interested. So I'm a researcher from Institute of Information Transmission Problems of Russian Academy of Science. This is a huge institute which has different types of research in different directions, and one of them is robotics. And I'm leading mobile robotics group there. So these are types of robots we are working on. So all these robots on the slide, these are robots which programmed by us, and we took part in the development of all of these robots. So as you can see, starting from really small indoor robots to huge autonomous buses and cargo vehicles. So we are performing research in all these directions. There are just some recent publication from our group. This is a geography of conferences. Within the last couple of years, we traveled a lot to scientific conferences to present our work. And there is just small overview of research fields we are working on. Why I'm telling you all that, because maybe somebody of you will be interested to make like master or bachelor, master thesis on this topic, or maybe like just perform some research with us. So if you are interested, just let me know during the course. We'll discuss possible like topics for research. So we are working on classification, detection, and object tracking. So these are videos from autonomous cars. You can see object detection, lane markings detection, So like road crossings detection and different types of algorithms we are working on. We also work on swarm robotics. This is a field we didn't discuss, but basically swarm robotics is when you try to perform a single task using a group of robots. It's also really hot research topic right now. It is not really new, but still evolving field of research. And for example, on the slide here, you can see algorithm we developed. This is a stochastic patrolling. So the main goal here is to patrol an area. So to visit every point on the map in a way that nobody from the side cannot predict where robots will move like next second. So you can see that robots are moving really unpredictably, but still they cover the whole area of patrolling. And this is types of algorithms we are working in our lab. So also, of course, there is navigation and data fusion, and this is my personal favorite topic. So it is a really complex to teach the robot to navigate through space. So it has to understand where it is and see obstacles. And for example, there are two examples of outdoor and indoor navigation. So indoor, you can see that robot is detecting walls and floor conjunctions and compares them to the predefined environment map to localize to determine its pose in space. And the same applies for outdoor. It is video from autonomous bus you could see before for this one. So it also detects lane markings, and given the map of environment, it can tell where it is. So we also work on visual odometry. As I said, this is a technology which was born in aerospace projects and rovers, but now it applies in autonomous cars, in modern autonomous cars. And here you can see that detecting features on the image, we can tell where we are in a space really, really precisely. And it is also still evolving area of research. Of course, mapping, because we use maps in robotics a lot. So robots are much simpler than if you can give a robot a map. So this is, for example, 3D map, and there is also map of lane markings. Yeah, and this was a short introduction why I'm telling you about robotics. And also, I think I have to mention that, just a second, if my internet will allow me, maybe not. So I'm also a CTO of a company called EvoCargo. So I just wanted to show you a website, but for some reason I just can't. But you can Google evocargo.com. I will send you a link to Telegram. So we are also in our company working on mobile robotics a lot. So we basically are building autonomous logistic vehicle for warehouses, for factories and other types of enclosed territories. And we also have a lot of research areas. We're also publishing papers. So if somebody of you guys are interested, you can just text me and we will discuss possible areas of research. And returning to our lecture, talking on mobile, or actually, as I said, mostly on wheeled robots, once again, I wanted to tell you why this is the right type of robots to study. So as you can see here on the slide, there are many types of wheeled robots, and I hope you all have seen a vacuum cleaner, which are really popular and common right now. There are also autonomous cars, there are also rovers and different types of delivery robots, or so-called last mile robots. So yeah, this is actually a cool video from Estonia. This is this small guy, delivery robot, is hit by the car and just random people are trying to save it. So this video shows that there are still many problems in mobile robotics and open issues which have to be solved. So these robots can be operated in the complex environments, but still. So why mobile robots? Because they're simple in construction and control. It is much simpler to build and operate a mobile robot or wheeled robot than a humanoid robot. So this small comics shows you the probable feature. My guess is there will be no Terminators looking like people, most likely there will be wheeled robots because they're just much simpler. Also, they're maneuverable. They can turn in place sometimes. They have small radius of turn, so they can operate and turn their direction fastly, and they're fast. If you could see these walking robots, they're still really slow. If we are not talking about Atlas, of course, it is kind of fast, but still, it is really clumsy. But all other types of walking robot, they're really slow. So and complex, as we already said many times. So these mobile robots, they're really common at the moment. After industrial robots, I guess they're the most common type of robot in the world. They're used a lot, and that is why we are studying mobile robots, because I guess the future is on mobile robotics. So this is a control scheme of modern mobile robot. As you could imagine, there are many types of algorithms have to be involved in operation of mobile robot. Starting from sensors, which allow us to perceive the environment, to know something about the world around us, and ending with actuators, which we use to travel through environment or to interact with the environment in some way. In between, there are many algorithms, but to simplify, we will divide them in three big categories, which we will discuss during this course. So for instance, next lecture will be on localization. So as I said, sensors allow us to perceive information about the environment. Localization is something, this is a type of algorithm which allows us to understand where we are in the world. And for that, we usually use map. There are algorithms which do not require map, but they're quite complex and we will not discuss them in this course, maybe just briefly. Usually we use the map of the environment, and then we use localization algorithms to answer the question where we are in this map. So path planning is the types of algorithms which allow us to plan our motion or our path through the environment. It is also uses map. This type of algorithm also uses map. It also uses information from sensors to know where the obstacles are. So in the end of this algorithm, we have a discrete and concrete plan of motion we have to perform to reach from A to B, or to move some object, or to perform some other action. And control is something which uses our motion plan and just performs actions. So control in terms of mobile or wheeled robots is actually how we have to operate our motors and steering to reach desired position. So path planning gives us a plan, and control algorithm just makes sure that we follow this plan. And the output of control algorithms is usually like current applied to the motor, or angle on which we have to turn our steering wheel to turn, things like that. And these things are directly sent to actuators in our simplified scheme, at least. So this is a simplified scheme, and this is a real one. This is from a robot called Stanley. Stanley is a really famous autonomous car, one of the first ones, one of the first famous ones, I have to say, because it's quite modern and there were many autonomous cars before Stanley. But Stanley became popular because it won a DARPA grant challenge. So there was a grant challenge organized by DARPA. This is a American defense agency. So they organized really cool competition for autonomous cars. It was back in 2005, and they had this competition many years in a row. And Stanley was the first winner. And actually, first year there was no winner. So first year, there was no team which was able to complete the whole track. And on the second year, on 2006, Stanley, this is a Stanford car, was able to run autonomously 50 miles without hitting any obstacle and won this DARPA challenge. And this is a control scheme or like algorithm scheme of Stanley. It looks quite complex, but you can easily find correlation because between our simplified and the Stanley real scheme. So for instance, there are sensors, many sensors used by Stanley. You can see there are laser scanners, cameras, radars, GPS, and other types of sensors. We will talk more on different types of sensors in a moment. So there is perception, as we said, so UKF pose estimation. This is algorithm of localization, this one. And this stands for unsended Kalman filter. We will discuss it on the next lecture. There is planning and control. You can see there is top level control, path planning, steering control, throttle control. So path planning is our path planning, and there are different types of control for different actuators, for steering, for throttle, brake, and so on. Different types of actuation car has. So you can see that there is a lot of correlation, and basically any autonomous car or mobile robot has the similar type of control scheme. There can be different types of sensors, different types of actuators, some different types of localization, but the whole scheme is really similar. And the last topic of today's lecture, so as soon as we started discussing this scheme, we will talk on different sensors types used in mobile robotics. So basically the first half of the course, we will talk on each block of this scheme. So today we are talking on sensors, next lecture is going to be dedicated to localization and so on. So we will discuss each type of algorithms and particular algorithms used to solve each of these problems. So starting from sensors, we can divide sensors by two categories. So by registered signal, there are active and passive sensors. So for instance, like camera is a passive sensor because camera doesn't emit any type of signal, right? It only collects visible light to project it on a screen basically, or store it in a digital memory. So camera is a passive sensor. And if you have some type of sonar, which is sound radar, it is active because it first emits some sound wave, then measures time between like emission and receiving back this sound wave and make some calculations based on it. So active sensors are usually more precise because they control the signals they emit. But there are many problems associated with active sensors. For instance, if there are no complex encoding scheme in these sensors, they start interacting with each other. If there are two sensors close to each other, they start interfere and spoil signal of each other. In modern sensors, there is a really complex encoding scheme, so each sensor is kind of unique, and they can distinguish between their own signals and signals of other sensors. So this problem is kind of solved, but still it is a problem because when we apply many sensors, for instance, when we will have like thousands or millions of autonomous cars, they all will use similar sensors and they will definitely interfere. So passive sensor doesn't have this problem. Also, there are two types of sensors based on registered value type. So there are really complex words, you don't have to memorize them, but there are proprioceptive sensors. These are sensors which measure something internal to the system, so internal to the robot. For example, our own speed or our own position in space. So if you measure something about yourself, this is a proprioceptive sensor. If you measure something about world, so distance to obstacle, temperature, or something like that, this is called exteroceptive sensors. So these are two types of sensors, but sometimes we cannot even tell about the sensor which type it has, because there are some sensors, for example, camera, which can be used both to determine something about ourselves. So for example, these space rovers, they use camera to tell where they are. and that makes camera proprioceptive sensor. But also they use camera to detect obstacles, and it makes a camera exteroceptive sensor. So sometimes it is really difficult to tell. But there are two big categories you just have to know, but you don't have to memorize these complex worlds. So there are many types of sensors used in modern robots. We will briefly discuss each type. Like it will take 10 more minutes, I guess. I hope it's okay for you. If you have to leave, you can leave earlier, and there will be recording of this lecture. You can just watch later. There is some question. No, it's not a question in the chat. Okay, so as I said, two types of sensors, proprioceptive and exteroceptive, also active and passive. So we'll talk about these sensors in more details in the next slides. And here I just wanted to note that cameras, LiDARs can be both proprioceptive and exteroceptive, as we already discussed. So this is a modern autonomous car again, and you can see that it uses different types of sensors. There are cameras, different ones, short, medium range radars, LiDARs. So each mobile robot is equipped with many types of sensors. This is actually a car from Uber, as I remember. It also uses LiDARs, cameras, radars, different types of radars. Also, there is always a wheel encoder. This is a sensor which allow you to tell how much your wheel is rotated. So you can also count rotations and approximately know where you are, or at least you can know your own speed. So there are many types of sensors. This is Audi autonomous car, also using a lot of sensors. And even not autonomous, just common cars nowadays have cameras, have radars, encoders, and many types. This is Uber again. So this is interesting. Again, if you have seen a vacuum cleaning robot, it looks really simple, but actually it is really sophisticated, and it uses all algorithms we will discuss in our course. So basically you will be able to build your own vacuum cleaner after the course, I hope, especially given the practical experience with robot operating system. So for example, there are ultrasonic sensors. So these are sensors sending ultrasound wave and measuring distance in this way. This particular robot has a laser distance sensor, or LiDAR. There is also, you could see that these robots can hit the wall, like physically hit the wall, and they have some type of bumper or button on the front. So this is a really button, and it is called physical sensor or pressure sensor sometimes. So they can tell either they hit something by this type of sensor. They also have cliff sensor. You could see this cool demos when you put this vacuum cleaner on a table, for example, and it never falls down because it has this cliff sensor. This is a basically distance measuring sensor, which can just tell that distance sharply changes, like fastly changes. And based on that, robot can make a decision that it reached the edge of the table and it has to rotate and turn back. They also have gyroscopes, accelerometers, so many types of sensors inside such a small and simple, I would say, robot. So we'll talk on all types of sensors a bit in more details, just for you to have an understanding how they work. So encoder is we'll start from encoder. It's an electromechanical device that converts angular position of motor to analog or digital output signal. So basically it is really simple. Encoders are usually attached to shaft of the motor, a rotating shaft. And there is usually light source, some code disk, which has holes in it, and detector. And basically by rotating, you can you get the pattern, some binary pattern where light is on and light is off because of rotation of this disk with holes. And then you can tell how much your motor is rotated based on counting of this dark and light periods. So there are more sophisticated encoders which use some complex type of encoding. This is used, for example, to tell to which side the motor is rotating, because if you just use the simple disk with holes, you cannot tell to which side you're rotating. You just see light and black spots, and they're similar invariantly to the rotation side. So there are optical encoders which use light and detectors. There are also magnetic encoders which use Hall law, Hall principle, and static magnets, just to tell that there is either magnet in front of detector or there is not. But the principle is the same. And also there are two types of detectors called absolute detectors. They maintain position value even when they powered off. This is a powerful feature. For example, if you have a manipulator and you rotated an arm and switched off the robot, you would prefer to know where the arm is when you switch it on. If you have just incremental encoder, you just cannot tell your initial position. But if you have an absolute encoder, they kind of remember the position they're in, so you can continue operation from the point you stopped. But in mobile robots and wheeled robots and in any type of car, you have encoders on your wheels, because car knows the distance it traveled, and it calculates it using encoders. So we just calculate rotations of the wheel based on these patterns, and then just integrate it in time and know how much we traveled. And car has simple incremental encoders, because for you it doesn't it is not important on which position your wheels are when you switch on your car. It just doesn't matter, because you will just rotate cars from any position. It doesn't matter. So cars usually have incremental encoders. Yeah, and this also some images showing how encoders work. This is a type of encoder with encoding. So each angle corresponds to some binary code. Because we have this complex disk with holes, we can encode different angles with real binary code. And there are many types of such encoding. You can see different types of these disks on the slide. So once again, encoders is something that takes motor shaft rotation angle as an input, and as output we can get speed, traveled distance, acceleration, and even yaw angle. Yaw angle is an angle of rotation of a robot in a horizontal plane. There is image, so yaw angle is a rotation about the z-axis, so in horizontal plane. And we can get it from encoders purely. If you have two encoders on two wheels of a car, you can just imagine a car. If you have two encoders on the right and the left wheel, by the difference of rotation, we can calculate how much car turned, right? So if left wheel moving faster than the right wheel, we know that we are turning. And we can even calculate how much we are turning. So such simple type of encoders, such simple type of sensors gives us a lot of information. So usually encoders are not really precise in big robots, in mobile robots, but they at least give us some rough approximation. So there are also internal measurement systems called IMU, VERO, IHRS. You can meet all these abbreviations, but we will usually call it IMU, inertial measurement unit. In this case, this is the most common one. And IMU is a sensor which actually has several sensors inside. It has accelerometers to measure acceleration, usually in all three directions. It has also gyroscopes, which allow you to use to estimate angle of rotation or your angular speed. Sometimes IMUs also have magnetometers and altimeters to tell the height, because these sensors are often used in quadcopters and different types of drones. Sometimes the height above the ground is important. That's why they also have these magnetometers and altimeters. And this group of sensors allow us to, they take as an input or measure linear acceleration, angular speed, and magnetic field, and allow us to estimate our own acceleration, 3D position in space via integration. So if we know acceleration, we can twicely integrate it and get distance traveled, right? And also having angular speed, we can get 3D orientation. And as you can see on the slide, this is a small, the cheapest one, accelerometer, not accelerometer, IMU, and it allows us to estimate its position in space. So the really popular nowadays type of sensor is called LiDAR, or light detection and ranging. It is used on mostly all autonomous cars in the world because it's really precise and it is one of the best sensors for autonomous cars. The simple is really, the principle of operation is really simple. So first LiDARs were operating as on the slide. So basically there is a laser rotating mirror. So by rotation, it projects laser to different angles. And each angle we send laser, it reflects from an obstacle, flies back, and by measuring time, it took the laser to fly forth and back, we can determine distance to an obstacle. So you can see here, the blue one is a LiDAR. It emits laser to different angles, and in the bottom, there are just points of measurements with calculated distance to obstacles. So this is a simple planar LiDAR. Nowadays, there are more complex 3D LiDARs. So apart from rotating horizontally, they have different lasers on different vertical angles. So we get kind of 3D picture like this. So this is a sensors measurement from LiDARs. Colors here are already some algorithm used to detect people, cars, and different types. This is called semantic segmentation. But basically the point cloud, you can see, this is a data from LiDAR, and you can see that it is really 3D. So this is a complex LiDAR with different vertical angles. And as you can see, it gives us really rich information on the environment. So LiDAR uses electromagnetic wave laser emission, and as output gives us point cloud, where each point has its distance and even reflected signal intensities. So apart from distances, laser give us intensities of signals in different points. And this is really important information for us because there are many algorithms which used, for example, to detect lane markings, because lane markings on the road, they have different reflection properties from the road itself. And we can tell just from a point cloud, which doesn't have any colors or something, we can have either it is lane markings or not. For example, here even you can see some lines, right? In yellow color, there are some more bright lines. And this is because lane marking has different reflection properties, and LiDAR can measure this also. So there are well-known ultrasonic sensors or sonars. They used in water robots a lot, but they also used in mobile robots. And I think you all have seen Parktronics in the car. This is a system which just allow you to park more easily. And this is exactly ultrasonic or ultrasound sensors. So they emit sound wave, again, measures the time it takes this wave to travel forth to obstacle and back to the sensor. They also have detector inside, which receives this emitted sound wave. And by measuring time for traveling of this signal, they can tell how far object is. They're not that precise as laser, but they're really cheap. You can buy them for $1, I guess, for like such system. They're used a lot in modern cars, and in mobile robots, they're also really used. So as input, they use ultrasonic signal. As output, they have distance to the nearest object. Yes, it's important for ultrasound that in LiDARs, we have a really narrow laser which measures one direct point. Here, we emit wave. That is why it has some radius, basically. And we cannot tell exactly where object is in some area. We just know that in particular areas there is object on particular distance, but we cannot determine where exactly inside this area. Yes. So the same principle applies for radio. You all heard of radars. It is the same, but only uses electromagnetic radio emission. So we emit radio wave. measure time it travels to object and back, and make some conclusion on the distance to obstacle, and also using Doppler effect, so the change of wave period depending on the speed of detected obstacle, we can also tell the speed of an obstacle. This is really practical and good feature of radars. And there are different types of radars. For example, on the slide you can see a really huge military radar, and this one is a small radar which is palm size. And this is radar which is used in car. So in modern cars there are radars which look like this. They're that big. So and also allow us to detect obstacles in front of the car. Of course, there is camera, and this is my favorite type of sensor because I'm mostly working on computer vision in robotics. So camera is really interesting because it's not like any other type of sensor. It is important to understand that camera is a projective sensor. It takes 3D world and projects this to 2D plane. And this is important when you develop algorithms. You have to understand that what you're working with is just a projection with all consequences. So what's cool about cameras is that apart from these all sensors, camera is passive. It doesn't emit anything. It just collects the light which is out there already, reflected light. Camera has really high spatial resolution. So even here in LiDAR, you can see that there are holes where we can just didn't detect anything, and this is a point cloud. Points are quite far from each other. In camera, we have like millions of pixels. So in terms of spatial resolution, camera is the most precise sensor, but camera on its own doesn't give us information on a distance. So we cannot tell just by an image how far obstacle is. And this is the main drawback of camera. We have to come up with really complex and sophisticated algorithms to use cameras for measuring distance. So camera collects reflected electromagnetic emission, and it can be not only visible light. For instance, there are X-ray cameras, there are infrared cameras, and infrared cameras is also really cool sensor because it allows us to see in the night. And as output, we have image, which we can use for different types of problems: classification, object detection, semantic segmentation, and many more. And there are also depth cameras. These cameras allow us to overcome the drawback that we cannot measure distance. So there are different approaches to measure distance with cameras. For example, there are stereo systems. This is somehow similar to our eyes. So people use two eyes to measure distance to obstacles because there is so-called parallax, the difference how we perceive with the left and right eye, and using this parallax or distance or angle between our two eyes, we can tell the distance to obstacles. Like recent studies show that we can perceive distance even with a single eye because of like some algorithms in our brain. But this is just a good analogy to understand how stereo cameras work. So because there is some distance between cameras, you see the world from different perspectives, and using the information about the distance between your cameras, you can tell the distance from cameras to the obstacles. There are also active stereo systems when we have some projector which projects a specific light pattern on the world, and seeing how this pattern changes depending on the world structure, depending on the distance to obstacles, we can also tell the distance. There are some systems where there is only one camera and projector. So maybe you know Kinect camera. So Kinect camera uses something like this. There are infrared projector, which projects invisible for our eye pattern, and there is infrared camera which detects this pattern, analyzes how it's deformed, and can tell distance to obstacles. And there are also time of flight cameras. So there is laser source which point by point sends laser signal, and there is camera which receives this signal, and again measuring time of flight can tell how far this point from the camera is. So there are many ways to use cameras. to measure distance and make it even more convenient to work with cameras. So this is example of depth camera. So we get in the end something like this. It is really close to what we get with LiDAR, but as a bonus, we also get colors, which can be used for some types of algorithms. So we again get 3D point cloud. So each point has its distance in space and color in this case. So, and that's it for this lecture. I hope it was interesting for you. There are some additional sources in the end you can read to find out more on sensors, on different types of sensors, how are they used in mobile robotics. So I really recommend you to read these additional materials because they're really, really cool and interesting. So basically that's it. If you have some questions, you can ask right away. Sorry for being late, for taking more time than I had to. Okay, so are there any questions?